Hey guys, last week we looked at potential fields, and I said if I dropped you anywhere in the solar system, eventually you're going to fall towards the sun and burn up and probably die. Sad face. But we want to know why that is, and we talked a little bit in the last video about the fact that if you are around a massive body, you're going to experience some force, and in fact the other massive body will also experience a force. And we said that that force is going to be equal to minus big G mm over r squared. This was Newton's universal law of gravitation. But what we want to do today is look at really what's going on energetically. Usually in physics, when you start thinking about energies and transfers of energy, you get a better idea of the underlying physics. It's much more insightful. So that's what we're going to do today. I'm going to recap what we looked at regarding potential fields last week. So if I get rid of you and your sad face, let's go back to this idea of our massive body. Because there's a force acting on any test mass that I drop near this massive body, there must be some potential to do work. And as I said in lessons, this is a bit of a cheat, if you like, but what we can say is loosely force times a distance, so force times a radius in this case, will give us a work. That's not strictly true, and I did actually tell you that in real life, in big boy physics, what we'd actually do is the work done would be the integral of f dr. So mathematicians, if you want to attempt that one, that'll be much more insightful for you. But as a cheat, and it is completely by coincidence, doing this operation, our gravitational force multiplied by a radius r gives us work. So let's look at that to begin with. So if I multiply my force by radius, that should give us a work, so F times R, and that will give me minus G m over just R, so the R's will cancel. So now we've got some work. So I could define, if I wanted, on this field, a point where the work done is going to be the same, or the potential energy is going to be a certain value, and I'd end up with a sort of contour map. But if you remember back to last week, there's a problem with that, because this, let's say I put in another slightly bigger mass, m prime, this equation has a dependency on m. So again, if I'm drawing contour maps for these guys, if I want to draw a scalar field, because energy is a scalar, it's going to have some dependence on m, and that's bad. Mainly because this guy A and this guy B, if they've both got their contour map, if you like, so they're both on Google Maps or something, their map of the field is going to look different because they have different masses, and we don't want that. So what we're going to do is we're going to remove the dependence on my test mass, and that's dead simple. All you do is divide by that test mass, little m. So if I bring this up here, that will give us the work per unit mass now is minus big G over R. And we're going to call this something new, so this actually is our potential, which is a big V. So if I shove this over here, I'll define this for us. Now, potential, gravitational potential, not to be confused with gravitational potential energy, they are different things. It's quite a weird concept, and it has a very particular definition in physics. And that definition is as follows. If I have a test mass at some radius r away from a gravitating body, the gravitational potential of that mass is the amount of work done per mass of this test mass that it would take to make this mass escape all the way to infinity. So obviously this test mass is experiencing a force towards the massive body. So to move further away from it, I'm going to have to do some work against gravity. I'm going to have to burn some chemical energy so that I can use a rocket pack or something like that. But I'm going to have to do some work. And we say that we want to go to infinity because that is the only place, and I will say that's the only place mathematically, not physically, because physically we know that my boy Newton said the gravitational force has an infinite range, so this is just a mathematical convenience. We're going to say this is the work done per unit mass in taking this test mass from a radius r all the way to infinity. We say infinity because that is where v is 0, so we're carrying it far away from the gravitational influence of this other mass. So that's our potential then, and that's worth remembering this definition because it's quite a weird one. So because this is a amount of energy or work per unit mass, this is very much a scalar field, as opposed to the vector field that we talked about when we talked about the field strength last lesson. But it works in the same way. We can represent this in a similar way. So if I have my body of mass over here, so big M, and in fact it's useful to describe the uniform case as well. So if you remember, we always have two cases. There is a radial case, so in circles if you like, and we have a uniform case, which physically is akin to being very close to the surface of the planet, so down here or something. And we know our equation in the radial case is V is minus big G M over R. So this equation only has a dependence on radius. So we can join up lines of equal potential quite easily. What shape defines something, a distance of constant radius from the centre? That's just a circle. So all we do is we can draw some contour lines. This, if you like, is exactly the same as a contour map. All it's doing is it's mapping lines of equal potential, whereas an actual contour map maps lines of equal height, if you like. So our potential will be concentric circles in the radial case, and the spacing will increase the further away from the centre you get. So I'll just mark a little radius here. So the further away from the centre you are, the weaker the field, and it behaves exactly the same as the last field we talked about. So spacing between lines tells us about strength. So if you like, the spacing down here is quite close. So close to the planet, it's very negative. And over here, where the spacing is further away, it's less negative. But remember, it is always negative over here. Always, always negative. And the reason for that is because, as we said last time, gravity is an attractive force. Therefore, if you want to escape this planet, you will have to put work in. You'll have to do work against it. So that's why. So spacing indicates strength, and obviously by looking at this, spacing goes up as r goes up, so it goes up with radius. In the uniform case, we know that we treat every position as being equal in field strength, so we're going to have the same idea. We're going to say it's pretty much the same potential no matter what distance r or what height r we are from the surface. So in the uniform case, exactly the same deal as with field strength, equally spaced, and that's it. It's nice and simple. Okay, so that is our potential. But what's actually quite nice, if we think about this idea as being contour lines, just like our hill, what we can do is we can start plotting what this will look like sort of graphically, or if you like, if we take a cross section sort of looking side onto this planet. So we can do this. So here is my graph, lovely axes as always. So radius this way, where if we carry on going that will go to infinity, and potential on the y-axis where here we have 0, and it is always negative, so it's below the axis. And what I can do is I can chuck in a planet, or in fact let's chuck in a star. So let's chuck this bad boy in. So this is the sun, and we know the equation of this graph is just going to be our potential equation. Looks like this, and therefore it's going to exhibit this 1 over our behaviour. So it will be asymptotic at 0, and it will be asymptotic towards infinity, so it will never actually touch either of these axes in reality. A slight subtlety is that you can't actually go below the surface of the sun because you'll burn and die. So what I should do is delete this and draw it properly, so it will look identical, except we stop at the sun. If you like, we can carry a dotted line over there to show that it does actually continue below the surface of the sun, but we can't actually get there. So this, if you like, is our potential profile, and we call this a potential hill. No, we don't. That's a lie. I'm lying to you. We call it a potential well because it goes down, but it is really similar in idea to our potential hills in thermal physics. There, we had to supply some thermal energy so that our particles could get over that hill. So this, if you like, was the activation energy, EA. In this case, basically, if I chuck a person somewhere, so little astronauts over here, what we can say is this astronaut at that radius, just dead simple, drawing lines across, is going to have some potential here, so VA, the potential of the astronaut. And obviously his potential is equal to the amount of work done per unit mass of this astronaut if I wanted to carry him from here all the way to infinity. So in fact what we're saying is he would have to overcome this height here, this change in potential, if you like. So this would be VA. And the amount of work done, because V is equal to the work done per unit mass, we can say the total work done he would have to do is just equal to mv. Or in fact, let's be real about this. This is going to be m delta v. It's just that v up here is equal to 0, v down here is va. So delta v is equal to just va in this case. So actually, the amount of work done we're going to have to multiply by this guy's mass. So if he's got a mass little m, it's going to be mva is equal to the amount of work he would have to do to completely escape the solar system. Okay, so that in a sense should hopefully give you an idea as to why it's negative. Like I said earlier, you have to supply energy to escape. Right, let's look at another example then. Let's say our astronaut, starts off near Earth over here, and he wants to move, he wants to take a space trip down to Venus. So he's at Earth here and he wants to go to Venus. So same idea again. Here he starts off at a particular radius, or he or she, sorry, I should say. Women in science. And he's going to move down this way and end up at this position. So this is where Earth is, this is where Venus is, and he's going to have some new potential here. So this is potential at Earth, his potential at Venus. So how much work do we do in moving him or her over there? Okay, so the first thing we want to do is, if we want to know the work, we know work is equal to the mass times the change in potential that's going on. And we know the change in potential is the difference between the potential at Earth and the potential at Venus, where Venus is more negative than the potential at Earth. So basically what we're going to do is just substitute that in. So his mass is going to be the potential at Earth minus the potential at Venus. That's going to give us a positive number in this case. So that's indicative of we've gained some energy, which is true, right? I could just plop this guy in Earth and he will eventually fall to Venus's radius. And we've got no qualms about that, so that's good. That's sort of proving what we're thinking. Okay, so that's potential wells, both moving closer and moving further away. We'll look at this a bit more in the next video, and we'll relate this actually to orbits, but I'll just leave you with one thing. Actually, for the solar system, what I can do is modify this just before I move on for each of the planets. So we could have Mercury, Venus, Earth, Mars. They're all red in this example. A bit further away, Jupiter, big bad boy, Saturn, and then the first blue one, the second blue one, because I can never remember which order Uranus and Venus are in. And actually what we can do is, because potential is a scalar field, if I have more than one source of potential, these all have a mass, big M. They're all different, but they all have a mass. They each supply their own contribution to this scalar field, which is dominated by the Sun. It's the most massive, it's huge. But what will actually happen is this field will have a contribution due to Mercury, have a little well. It'll have a bigger well for Venus. It'll have a bigger one for Earth, one for Mars, quite a substantial one for Jupiter and Saturn, and again for blue 1 and blue 2. Oh yeah, and there's Pluto. That's not a planet, so get out Pluto. Sad face. And what I can do is actually just combine these to draw the overall potential well for the solar system, which would look something like this. So the blue line is our potential for the whole well. So I can delete these red lines now, and it will look something like that. So this is quite a complex potential, but hopefully you can get the idea. If you're a person and we start off at Earth, which is here, we actually start off down here right in this well. So if we want to go anywhere, we've got to get out of this well first. If we want to go down here, that's fine. So we'll actually gain some energy in doing that. But if we want to go up to one of the planets further away, or even if we want to escape the solar system, we're going to have to do even more work once we escape our little potential well in this huge potential well towards the Sun. And this is why spaceflight is so difficult, because if we get lucky, say we were going to Mars, we've got to get out of our well, and then we've got to time it just right so that we fall into Mars's well and end up here. And if we don't, what happens is we'll overshoot and we'll fall back down and we'll burn and we'll die. We'll fall into the Sun. And the same goes in the opposite way. If we want to go to another planet, we've got to time it, we've got to get out of our well, and then just time it just right so that our trajectory lets us fall into that well. And if we miss, we're going to fall towards the Sun and burn up and die. Rocket science is so precise. There are millions and millions of dollars that go into it to make sure that doesn't happen. So next time you're thinking about NASA and space flights, it is incredibly difficult, even though the physics is well known. There are some really high levels of precision going on in their calculations to make sure our astronauts arrive there happy and alive. Right, okay. So in the next video, what I'll look at is I'm going to link our two fields, our scalar field V and our vector field G together. These are actually very tightly interwoven. And then finally, we'll talk about things that go around in orbits. So I'll see you next time. Thank you very much.